This is the Facebook Hacker Cup 2021 qualification round. This is the first problem. We have some string with uppercase letters, and we want all the letters to be the same. We can replace a consonant with a vowel with a consonant, or a consonant with a vowel. And so the question is, how many replacements do we need to make them all the same? Okay, so like ABC we can do in 2. Turn B into A and C into A, I guess. F, right, it's already all the same. Banana, let's see, we can replace the B's with A's, or the consonants with A's. Okay, so I think this one is pretty straightforward. Basically, we're just going to try all possible letters that we could end up with and see which one is the best. Make a list of vowels. A, E, I, O, U. U minus A. And I guess for consistency, it's A. They are both vowels or non-vowels. We have to take 2, so we have to go back and forth. Take 1. And I know we can just print out the answer. So what format do they want? Is best. Yeah, it includes vector. Insert. All right. Uppercase letters. Okay. Okay, tell us what the right answer was. Oh, I see. Okay. Let's see. Oh. That is kind of annoying. Uh, let's see. Yeah, I guess they don't tell us if we're right or wrong here, which is a bit annoying. But we passed the validation, so that's a good sign. I don't know. Kind of hard to tell how correct this is. Yeah, we'll just go ahead and assume that it's fine. Okay, so this is a variation on that problem. The difference is instead of like consonant to vowel or vice versa, we just have a list of rules of what we're allowed to change. So like we can change, I think, a B to an A or a C to an A. See, in this case, we can change an A to a B or an A to a C. So like this case is actually impossible because we can't change the B or the C to each other. Right, F is still take 0. Banana can change the B and the N to A's, so we can still get the same solution, so on. So similar solution. We basically need to find the cost to change each letter into each other letter, and then we can do the just try all possibilities again. Okay, so we're given T, S, and then K. Plus powerful rule, I guess. Yeah. So those are all the rules. And now we want to do all pairs shortest distances with void which all. So this is a pretty cool algorithm. So 3 lines of code. And the idea is it's basically a DV algorithm. So you're considering like each intermediate vertex K. EIK, the current path from I to J or the path through K. I believe that's right. Of course, you can always go from self to a self plus 0. E from SI to S. sample. Just look at Floyd-Warshall, make sure I got the order of the loops correct. Yeah, so we're sort of adding k to all the possible paths. So either it's like the current best path that goes through these vertices, or it's a path that uses k. Yeah, so for k, for I, for j, this thing, this is the same as just ij is the min of this and this. So that is Floyd-Warshall. And then we just try all possible final characters and figure out the total cost together. Okay, let us validate. H.1. Okay, has been validated. Let's get all this crap. Cool. Let's do it. The output file a2.out2 and the source code a2.cc. Alright, this is 40 things, -1, 61, -1, 2475. Is that even possible? I guess it could take 25 of substitutions times like 100. Yeah, so I think you can get up to 2500. Oh, times 99. Yes, okay. So that's like the maximally bad case. Well, it's a little annoying to locate that specific test case, but it should be fine. I think if we pass the validation, we should probably be okay, and we pass the sample as well. Right, so for each test case, read in the string, read in k, read in the rules, right? So this is like the minimum number of transformations to turn I into j. So I guess, default, we can turn I into I in 0 steps. And then you get all our rules, and all the rules are supposed to be 2-character strings, which is like you can turn A into B. So we can turn A into B in 1 step. And then we can use Floyd-Warshall to figure out how many steps it takes for any pair, right? Not just the ones that are directly connected. And then we can just try all possible, right? So we need the whole string to be the same character. Just try all possible characters for each character in the string, figure out how much it costs to turn into that character. And yeah, our final answer is just the minimum across that. And if it's impossible, well, we know that because the cost will be big, right? We calculated that the maximum possible cost is 2475, so if it's bigger than that, that means that it is impossible. And in that case, we should print out -1. and otherwise we should print out the cost. I guess one thing to think about here is overflow, but like LL can hold up to like 10 to the 18, so like 10 to the 9 it's not going to be a big deal. Yeah, so I think that's all there is to say for problem A. Let's look at problem B. Okay, so we're on an n by n grid, and we're playing tic-tac-toe, basically, except there's no diagonals don't count. So if it's a row or a column, you win by placing all of your symbols. So diagonals do not count. And so we're in the middle of a game, and I see we have dot x or o, it's the current state of the board, and we have an equal number of x's and o's, and the game is not yet over. Okay, and we are going to cheat. Oh, that's not good. Okay, so how many x's can we place to win immediately? And how many ways are there to do that? Okay, so the minimum number of x's is just, basically we're going to try all possible rows and columns and figure out how many x's you would need to complete that row or column if it's possible. If there's an O in that row or column, it's not possible. And that's going to be the minimum number of x's. And then the number of ways is just the number of rows and columns that you can complete in that many. Because there's no point placing any x's like not in the row or the column that you're going to win in. So here, all the rows and columns have an O in it, so we can't win. Okay. So let's just do that. So n. And so question marks. Okay. Let's see, it's a dot. The cost puts it by 1. So for each of the valid rows, I'll figure out the each cost. And you guys are going to do the same thing for the columns. And I don't know, there's some code duplication here. That's okay. A little bit sad to copy paste all this code, but whatever, I guess. Okay, so we've done all the rows, we've done all the columns. If that's possible. some periods and stuff. Steam, third string, stood. Okay. Let's give it a shot. That does not look correct. Interesting. Ah, that's actually the input. Well, that might be useful. How about now? 1, 1, 1, 2, 3, 6, 2, 2, 1. Possible. 2, 2. Okay, that's a little bit tricky. It's the same X that completes both this row and this column, so it doesn't count twice. Okay. Something like that. Pile. Closing angle brackets there. 1, 1, 2, 3, 6, 2, 2, 1, 1, impossible, 2, 2, 1, 2. Okay, looks like we got the sample, although that case was a little bit tricky. Let's see, we got okay. Cool. Looks like we passed validation. So let's get the real thing a try. Wait. All right. D dot out 2 and D dot CC. Okay. Did that successfully submit the output file that we wanted to submit. 50, 100. I think that must be the case of a totally blank board. Yeah. Yeah, so I guess the trickiness here was, I guess this only happens if it's one square, but one square might complete both a row and a column, in which case it only counts once. So I kind of really overkilled that by just keeping track of like literally the set of squares to complete a row or a column. And so, you know, the answer, if it's just like one square that completes both a row and a column, it will only appear in this set C once, because, you know, this will be the same. Like sets only store one copy of each thing. So that's kind of a very like brute force way of implementing this. You could do a smarter thing where you like explicitly, you know, keep track of like if this one square completes both a row and a column, like decrement, you know, the answer by one or something. But you know, this is simpler in some way. I mean, the work the computer has to do is more complicated, but it's simpler to think about. This is like obviously correct, whereas like being clever about tracking like that single square, you know, you could mess up. So yeah, it's relatively straightforward algorithm here. Read in T, read in N, read in the board. Forgot to read in the board initially. Then, you know, this is the minimum number of x's we need to place to win. So initially I'll just start that at infinity. And this is the sets of x's that we can place to win. Right, so this is a position on the board. This is a set of positions on the board, which is like one, the way to win in one way. And then this is like all of the ways to win. And then, so we'll just try all the rows. This is like, can you win on this row? And if so, which x's do you need to place? So if it's an empty square, then you need to place an x there. And if there's an O on the row, then you can't win on the row. If you can win on the row, then we can check if this is a better solution than what we have so far. So if it requires less x's, right? Remember that s is the set of x's that we place. Okay, well then the best so far is like this many x's, and the number of, you know, the distinct solutions that we found is just this one. If this is equal to the best number of x's so far, then you can add it to the set of solutions. And then basically just the same thing for each column, right? Is this column, can I win on this column? Which x's do I need to place to win on this column? So if it's an empty square, I need to place an x there. If it's an O, then I can't win on the column. If I can win on the column, if this solution is better than my previous solution, update the size of the best solution, update the set of best solutions. If it's equal to the best solution so far, add it to the set of best solutions. If we didn't find any good solutions, then just print out impossible. Or, if all rows and all columns were not possible. Right, otherwise, if anything was possible, best is going to be like m was 50. So it's a million, definitely not good. Print out how many x's we need and like how many different ways to place them in the x's that were. So that is it for B. Let's look at C. Okay, so we're going mining. We have n caves, n minus 1 tunnels, and each cave is reachable from the first one. So that means that we have a tree, right? We have n minus 1 edges, and the graph is connected. And any connected graph on n minus 1 edges is a tree. No cycles, right? Because you can only connect like two, each edge can only connect two things, and there's like n things that need to get connected. So each edge can reduce the number of connected components by 1. We start out with n connected components, we need to get it down to 1. So like all the edges need to connect unconnected components. That means there can be no cycles. Okay, each cave has a certain amount of gold. So we're going to start at cave 1, drive around, go back to cave 1, and exit with all our gold. Okay, the tunnels, you can only use each edge at most once, but you can visit a vertex multiple times. And we can drill exactly one extra tunnel. So the question is, we start at cave 1, we go around for a while, get back at cave 1 to exit. How much gold can we get? Okay, so here we can get 30. Start down to cave 2 and then drive back out. Here we can get 3 by like going through here and then driving back out. You'll notice that we're always going to use our like free tunnel to drive back out. So basically, we're just going to follow one of the branches of this tree all the way down, and then drive back out. Okay, so the question is, what is the minimum? Or what is the best branch of the tree to go down? Okay. That's going to give us our maximum amount of gold, because we have to use our free tunnel to drive back out, right? Because once you go down one of these paths, there's no way back, right? The tunnel's already been used, and because it's a tree, there's no way back later. So we have to use our free drill to get back out, and that means that we just, basically get to traverse like one edge of the tree. Yeah. Okay. So basically what we're going to do is, it's almost, I guess it's not really even a DP, but we're going to traverse the tree sort of leaves up. That would be in a, I guess it's a DFS. And at every subtree, we're going to find out like what is the best path if you started at the subtree, and then the answer is going to be the best path if you started at 1. Okay, so we have n. Let's see. And every vertex has a different value. CI equals CI. So these are 0 or 1 index rather. Yeah. Okay. So we're going to compute the parent and like the best score. Let's see. Be a global variable. So certainly we can collect x. And we can collect whatever the best thing you can see is. Guess we don't really need this for vector. Might be it actually. The IR stream include vector stir. Let's see for actually need the edges of the tree. Right. So let's try out the sample. Uh, 102188 is completely wrong. Okay. It's 30. Okay, closer. Oh. Huh. Should have read these examples more carefully. I was mistaken about how to solve this problem. Yeah. Okay, I guess you get like the two longest branches. Because in this example, right, you drive to the bottom of one branch, and then you tunnel to the bottom of another branch, and then you drive back up. That makes sense. Okay. Well, that is more complicated then. Well, it's glad you have examples. Yeah, same thing. Okay, So we need the two largest branches, and they need to be from different children. I see. Okay, it's just that the root is special, I think. If you're not the root, then you just want the single largest branch. I guess just that. $30, 4, 3, 12, 32. $30, 4, 3, 12, 32. Okay, that's a good sign. Those are some pretty big numbers. Okay, pass that example. How big do these numbers get? At most 20 million. So there's not really any chance of overflow here, right? 20 million times 50 is 100 million. No, billion. It's all much smaller than 10 to the 18. Okay, so we should be fine. Yeah, so we already validated, so let's download it. The thing that doing with password is kind of cool, even though I'm not really taking advantage of it. It's for people with slow internet, right? So you can download it. You don't need to spend part of your 6 minutes actually downloading at this point. Okay. 1.02. Actually, the one with the phone. Oh, I guess this is why we check that we actually went with the right thing. It's 35, right? did in fact submit this file, which, I don't know, pretty hard to tell if this is right or not. I'm just looking at it. The answer will be 0. That seems, I see, it can be because the C's can all be 0. Fascinating. No gold in that mine. That's too bad. Okay. Well, that seems fine. Oh yeah, we can build the solution. Check for any bugs. Okay, so we read the number of test cases for each test case. We read an N. We reset C. Because there are multiple test cases and we're using global variables, it's very important to make sure that we reset E, P, and C on each test case so they don't equal each other. So we reset C. We read in C. We reset E. We read in E. It's 1 index, so we can put it to 0 index. The edges are bidirectional. And then we're going to compute a parent vector, which initially is all -1s. Okay, and then we're going to root the tree and compute the answer at the same time. So C1 is supposed to be the best branch of any child. C2 is like the best branch of a different child. The point being that we can't use the same child twice because we would need to traverse the edge between ourselves and that child. Right, so the optimal thing with one tunnel we're claiming is to like go completely down one branch and then tunnel over to a different branch and then go completely up that other branch. But they have to be like, the branches can't share any edges, right? So they can't go through the same child. So for everything other than the root, we just want the best branch down from it. And then for the root, we want the 2 best branches for different children. Okay, so we're going through all our children. If in fact this is our parent, skip that. Mark down that we are the parent of the child. Compute the best branch coming out of C. Okay, if that's better than our best branch, then our second best branch is our previous best branch, and our best branch is this guy. And if it's better than our second best branch, then that's our second best branch. Okay, if we're the root, then we want ourself plus the best branch plus the second best branch. If we're not the root, we just want ourself plus the best branch. And that is it, basically. Let's see, like why this should be true. I don't know. I guess I feel a little bit bad claiming that it's intuitive when I said something wrong before. Right? I thought you should just go down one branch and then go back to 1. But obviously, it's much better to go down one branch, go to the bottom of another branch, and then walk back up to 1, get more gold along the way. And I don't know. Is it clear that that's the best you can do? Guess. Right, so certainly you want to go down to the bottom of some branch first, because you can go anywhere after you tunnel. So if you cut out early, you're just wasting all the gold below you. And you need to tunnel somewhere that you can get back to the exit, escape. So it needs to be somewhere in the subtree of one of the other children, not the first child again. And you might as well, you need to follow a straight path back to the root, so you might as well go to the most expensive one. So yeah, I think it's pretty clear that that's what we should do. Okay. Chapter 2. It's pretty similar. Again, we have this tree of gold. Again, we can only traverse each edge once. But instead of 1 tunnel, we can do K tunnels. Okay. Yeah, so it's basically entirely the same, except instead of 1 tunnel, we get K tunnels, which, might complicate things. Okay, so I think it's a similar idea. We want to like drill to the bottom of caves and then traverse to other segments, but it's a little bit more involved, right? So, you know, we have this tree, and so the optimal path is, you know, we go down here, and then we teleport somewhere. I guess one interesting wrinkle is we don't need to go back up to the top initially. So like we could teleport here and go up there, and then teleport here and go back up. So that's like, you know, a possible solution with k equals 2. So I think what we should do is it's a basic figure. Okay, so I'm gonna disassociate every edge. Um, yeah, so maybe it makes the most sense to think of this as a tree DP, right? Where the DP question is, yeah, so like you're at, let's do it here. How much gold can I collect from this subtree using a else? Is that quite right? Sometimes you enter the subtree sort of from the bottom. And also, there's the question that sometimes you have to get out. I think about decomposing this tree into paths. Just like uh, every parent is only, every node is only connected to like its most profitable child. we can traverse two paths from the root, and then like k minus 2 other paths in the tree. K minus 1 other paths in the tree, I guess. Something like that. And it's still 50, right? Yeah. I think for every tunnel we drill, right? Basically, like our optimal path is going to be like down somewhere, and then tunnel somewhere, and then like up and down here, tunnel somewhere, up and down here, and then tunnel somewhere, and then go out. So, like, pick some nodes and do like the best two paths of each of them. Something like that. The issue is these paths should not cross at all. On the other hand, all these numbers are very small, so maybe we can afford to do something really dumb. Like, is it true that we always want the longest two paths in the root? If that is true, then we could like basically cross off all of those edges and then recurse on the remaining tree. Okay, I think I have an idea for this one now, which is yeah, basically you can spend some unit k to like add. You can spend one of your tunnels to so sort of the default is that you get to go down one edge from a node, but if you spend a tunnel, then you get to go down 3 edges. If you spend another tunnel, then you get to go down 5 edges. And I guess for the root, the default is that you get to go down 2 edges. And also you have to spend a tunnel to do that. So that one you're forced to spend, right? This is like in the C1, that was the only tunnel, but in this one, you can spend an extra tunnel anywhere, including the root, to go down like 2 more edges. So I think that's the idea. The input has n and k, and we have to spend an edge at the root. Yeah. Something like this. So yeah, the root is just going to be responsible for computing the parent and children, basically. And then we'll do some more work in this DP. Right, so you have some budget, and you can either assign your budget to your children, or you can use it to sort of access more children. Is it? Okay. A little slow. But maybe it's fast enough to compute. Yeah, example 10, 10. Okay, well, it fails the very simple case. It's totally going. Okay. There's some gold here. No, maybe that's not right. No, that's not right. We're gonna get our gold once we're done with all our children. Definitely 0. It can be 0. Oh. 19. Mm, 43. Three and 4 and 8. 4 goes to 5 and 2. 8 goes to 9 and 6. And 6 goes to 7. Two tunnels. So basically we should miss out on 9. Yeah, okay. Not really confident this is right, to be honest, but I don't know. Pass it the sample, pass it the validation. And I'm not too fussed. I need to only get one problem right to pass the qualification round, and I'm pretty sure I got one of the problems right that I already did. So we're just gonna go for it. If I really wanted to make sure I was gonna solve this correctly, I would probably want to think about my code a bit more first. But instead, we are just gonna try something. Let's do that too. Not worried about runtime. Correctness. And indeed, the runtime is fine. T2.cc. Double check that we submit the right file. So the answer should be up to like 100 million, which, I don't know, seems reasonable. Okay, so let's see if we can justify this. It's not right. Okay, so the first thing, so how does the solution work? Okay, so for each test case, we read in n, we read in k, we read in how much gold is at each vertex. Then we read in the edges. Then we root the tree, which means for every edge, or for every vertex, we give it a parent and children. So rooting is very simple. You just go through all of your edges. If this is not already your parent, then mark it as a child. Mark that you are its parent and recurse into the child. So we sort of assigned every edge direction, right, pointing down from cave 1, just starting cave and ending cave. Okay, so we root the tree, and then a special case if k is 0. If k is 0, then we can't dig into anywhere. We'll never be able to get back out. So in that case, the answer is just how much gold is at the root. And otherwise, we do this DP. So let me try and explain the DP if I can. Okay, so we're at some node. We're considering some prefix of our children. We have k free tunnels here, and we have f free children. So this f might be unclear. I'll try and explain it as I go. Okay, so if we're not considering any children, well, then you just get the gold at this node. This is just memorization. Skip this for now. Okay. Right, so basically, yeah, we're considering like what we can do with up to some specific child. Okay, so one thing you might do is just ignore that child entitled, right? So just recurse unlike the rest of your children. And then nothing else changes, right? You're still at node X, you still have k tunnels, and you still have f free unlocks. Okay, the other thing you might do is actually do something with that child. And we're going to enumerate how many tunnels you're going to spend within that child. So essentially, tunnels let you recurse into children in some complicated way that I'll try and explain. And so the question is how many. Anyway, if you spend tunnels on a child, then you get to explore more of that child's subtree. It's the high level idea. Okay, so C here is an index into my children. So the actual child is, my children, the Cth one. Okay, so one way that you can go into a child is if you were already planning. Right, so this is the structure of an optimal path. So F is how many of these paths are coming out of a given node, essentially. Yeah, that's the right way to think about it. So the point is, we can either just like have one of our branches coming out of ourselves be through this child, right? So that's this first, that's this first case. And so to do that, we need to spend, one of these branches. If we don't have one, so you can buy 2 branches for 1 tunnel. So if we don't have one, we have to buy one. Okay, so if we do that, then we can recurse on the child, right, for all of his children, however many tunnels we gave him, and he has 1 branch expected to come out of him, right, which is like the remainder of this guy. And for myself, I can process my other children, and I have this many, like basically all the tunnels I gave to that child I can't use anymore, and I may have had to spend a tunnel to buy 2 branches if I didn't have any branches left. So that's what this term is. And then if I bought a branch, well, I spent 1 on this child and I have 1 left, and otherwise I just spent a branch. Okay, so that's this first case. And then the other case is that like my child is going to be one of these intersection points, right? So it's not that I'm going into my child, but like later we're going to tunnel to some leaf from my child, and then we're going to go up to the child and down to some other leaf. Okay, so if that happens, then you go into the child and you can go through any of its children. We spend k tunnels there, and we have 2 branches coming out of that child, right? This one and this one. And in that case, we don't spend a branch. We have to spend like a whole tunnel, right? Which is like this tunnel. It's the one that we're spending. So we can either spend a branch resource or a tunnel resource. And if we spend a branch, then like the child gets 1 more branch, and if we spend a tunnel resource, the child gets 2 branches coming out of it. Yeah, I guess maybe that's the complicated thing about this idea. It's like we've introduced this branch resource that was not sort of in the problem description. Okay, and then so I can recurse on the rest of my children, get 1 less tunnel to pay for the 2 branches in my child, and then however many tunnels I gave my child, I can't use them with my other children, and I didn't spend any branches on that. So yeah, those are the ways that I can spend my resources on this child. Here are all the ways that I can spend my resources. Just ignoring this child. And so all those possibilities, whichever one ends up the best, that's my answer. Okay, and then the normalization is pretty straightforward, right? This is a pure function of these 4 variables. So, as usual with normalization, if you've already seen a call to DP with these arguments before, we can just use the previous one. So we keep a memo table of that, and we just compress these arguments down to 1 dimension. It doesn't really matter. You could also have a 4-dimensional DP table. Anyway, we can compress them, right? We know that n is at most 50. I see, in all my babbling, the timer expired. Well, hopefully it was right. Anyway, n is at most 50, so x is at most 50, c is at most 50, k is at most 50, and the number of free branches we have is at most 2, because we only buy a branch if we have to, and you buy 2 branches at a time. So you only buy if you have none left. So branches either 0, 1, or 2, sort of all that. So let's just compress into this 1D space. And if we've already computed an answer for this, we can just memorize it. So construct the memo table and then run DP. So initially, at the root, we're forced to spend a tunnel on 2 branches. So that's why this is k minus 1 and 2. And that's why it's special case k equals 0. And other than that, you're at the root and you can go through all the children. And then just put out the answer. So hopefully that makes sense. I guess I sort of explained it, but didn't really justify why this was correct. I don't know, I think it's like sort of this picture, right? The optimal structure is just like these sort of V shapes in the tree. And you can have multiple V's coming out of a single vertex, right? That's like 4 branches. Like these tunnels, that would be valid. You don't get to count this guy twice. It's fine. So yeah, I don't know. That translates into this, I think. Yeah, I don't know that I have too much more to say about like why exactly this makes sense. And yeah, I guess the key concept here is like introducing this additional branch resource. Which yeah, you spend tunnels to get 2 branches essentially. Okay, well, hopefully that's right. I guess I'll get to see in a couple days. And yeah, thanks for watching.